Bonjour and welcome to these office hours for week 2 of this 8-week class on functional analysis on Coursera. I'm at my office here at Central Paris where we have wonderful weather, and I hope that you have some great weather wherever you are in one of the 149 countries where students have registered for this class. This week we talked about metric spaces and norm spaces. And we saw that if we have a norm space or a metric space, then we have a topological space. Therefore, we have convergence, which is quite important, of course. What I would like to address in these office hours is first the question of what is a Cauchy sequence. And we had quite a few questions on the forum about what does this really mean to have a Cauchy sequence. That's a very good question. What does this mean? I mean, we understand the for all epsilon and the p and the q's and the whatnot, but what does this mean? So I'll answer this question, I'll try to answer this question. And then I will talk about compactness and sequences. And I will give you a preview of what might happen next. So let's get started. Let's talk about Cauchy sequences. So we all know the definition of a Cauchy sequence now. I mean, for all epsilon, there exists a rank after which I can make sure that the distance between two elements of the sequence is smaller than epsilon. Okay. What it means is that no matter how small of a distance between two elements you choose, no matter how small you want this distance to be, you will achieve to get this distance smaller than this epsilon. So we're almost saying, I mean, what I'm going to say is, it's like a hand waving here, but we're almost saying that, okay, at some point I'll almost make this sequence constant. It won't really be constant because it can still vary by an epsilon or epsilon over 2. I mean, it can vary very, very little. So what I'm saying is that at some point I will almost make this sequence, I mean, constant. So what we're saying is it's almost converging to this constant, right? It's going to converge. But the problem is that your space might have a hole. You might want to converge, your sequence might want to converge to a point which is not in the set. You see, that's the main problem. You may have a Cauchy sequence which does not converge into space because the space as a whole, it may not be complete. You see, if you have a complete space, then Cauchy sequences will converge. But if you have a non-complete space, then you may have the Cauchy sequence that will want to converge to a point which is actually a hole in the space. Let me give you an example. If you've got the development, the decimal development of square root of 2, like 1, 1.4, 1.41, 1.414, and all of this, right? I mean, this sequence is a Cauchy sequence, and you can verify that you can make the distance between two elements of the sequence as small as you want. I'm choosing the usual distance function of r here, and you can make this as small as you want. Say, I want the distance between two elements to be smaller than 10 raised to power negative 100, which is very small. Well, I will find a rank after which this is true. So my sequence is a Cauchy sequence. Yet, my Cauchy sequence wants to converge to square root of 2, which is not an element of Q. So we're in a situation where we have a Cauchy sequence that will not converge. You see? So that's the trick. So a Cauchy sequence, think about it as a sequence that almost becomes constant, wants to converge, and hopefully can if your space is complete, but may not be able to converge if your space is not. Okay, so I hope this clarifies what is a Cauchy sequence. And of course, if you have a converging sequence, then it will be a Cauchy sequence, right? I mean, if you have a convergence sequence, say it converges to L, then the distance between UQ, I mean UN or UQ or whatever you want to call it, and L can be made smaller than E epsilon, right? Now, if you look at the distance between UQ and UP, then you can make it smaller than the distance between UQ and L plus the distance between UP and L, right? I mean, this is the triangular inequality here. And if both of these distances can be made smaller than epsilon over 2, then you can make the distance between UP and UQ smaller than epsilon. So what I'm saying is that if you have a converging sequence, automatically it is a Cauchy sequence. If you have a Cauchy sequence, on the other hand, then it may or may not converge, because you may have the problem of the hole in the set, in which case the set is not complete. But if you have a complete space, then of course your Cauchy sequence is going to converge. Alright, so that was hopefully, I hope this answers the questions that were asked in the forum, and this is how to, would like to make sure that you understood what it means to be a Cauchy sequence and why completeness is important. Okay, now I would like to address something else. I would like to address compactness and sequences. If you read Anna Rozanova-Pira's document, you know that if you have a compact set and you have a sequence in this compact set, you can always extract a converging subsequence. So let me repeat this, especially for the people who did not read the PDF. So I'm going to re-say that so you know. I'm saying that if you have a sequence in a compact set, then you can always extract a converging subsequence. And I'm going to give you an example now. If you look at the compact set -1, 2, well, -1, 2 is a compact set. First of all, it's closed and it's bounded, and actually, if it's closed and bounded in Rn, then it's going to be compact. But otherwise, if you don't know this, you can read a PDF about that. But if you don't know this, simply you can just adapt the demonstration, the proof that we did last week when we proved that 0, 1 was a compact set. Then you can adapt it to -1, 2. So in any case, -1, 2 is a compact set. And what I'm saying is that let's choose the sequence un equals -1 raised to power n plus 1 over n. Now this sequence, here are the terms of the sequence. For n, obviously different than 0. What I'm saying is that obviously this sequence does not converge. Really, obviously it does not converge. But we can extract a subsequence. Let me drop every other term. Okay, they're dropped. You see, this subsequence converges to 1. Okay, so as you can see, we have a compact set. We have a sequence in this compact set, and one which is not converging. If it was converging, then every subsequence is converging. That's old news. But we have a sequence in this compact set, and I managed to get a subsequence that will converge. Okay, all right. And that's the case for any compact set. For any compact set, you have a sequence. You can always extract a converging subsequence. Now, let's look at the unit closed ball. Well, if it's unit, it's going to be bounded. If it's closed, well, it's going to be closed. So the closed unit ball is going to be a compact set if you are in a finite dimensional space. Again, remember, in Rn, if you have closed and bounded, it means compact, right? So if you are in Rn or any finite dimensional space, you have the closed unit ball, which is going to be compact. Therefore, if you have bounded your sequence by 1 or by any other number, and then you just divide by this number and whatnot. So if you have a bounded sequence in this finite dimensional space, you will always be able to extract a converging subsequence. That's a great result if you think about it. Let me just say it again because it's so great. You have a bounded sequence, right? You bound the norm of the sequence, and what you're saying is that if you manage to do this, you can extract a converging subsequence in a finite dimensional space. So that's a great result. If you are in an infinite dimensional space, things get a little trickier because the unit ball may not be that compact after all. Actually, let's look at this example here. Let's take L infinity. you know about L infinity because we discussed it, and we discussed LP spaces this week. Look at this function fk. You see fk, well, I just give you the graph so you can find it. Fk, the norm of fk is, in L infinity, is going to be 1 for any k. So obviously the norm of this sequence is going, every element is going to be bounded by 1. Yet, you will not be able to extract a converging subsequence. Try to do it. You'll see that this peak here is going to move to the right, and no matter what you do, you will not be able to extract a converging subsequence. So you see, we're in a situation where we have a bounded sequence, but we can't extract a converging subsequence. The reason is that the closed unit ball in L infinity is not compact. Okay? So again, finite dimensional space, the unit ball, closed unit ball, is going to be compact. So if you have a sequence which is bounded, you can extract a converging subsequence. But if you have an infinite dimensional space, you have a bounded sequence, you may not be able to extract a converging subsequence. And I said I would give you a preview of what's going to happen. We are going to find a topology for which the closed unit ball for these infinite dimensional spaces are closed. I'm compact. Are compact. So if we find this topology, it means that we'll bound the sequence. If we can find a way to bound the sequence, then we will have convergence in this topology, in this new topology. Well, this new topology will be called the weak topology, and the convergence will be called the weak convergence. And we will talk about that soon. So go back to that very, very soon. Okay? Well, in any case, I hope that you keep enjoying this class. I certainly do, and Anna and all the team is really being wonderful, and we all enjoy doing this with you. So we hope you keep enjoying this class, and please do not forget to submit your quizzes, to submit your writing questions, and also this week to grade your fellow classmates' writing questions for last week. It's important to do that. So I hope that you keep enjoying this class, and I will see you next week.